title in English, sustainable development and maintenance of code extensions and simulation setups for open source flow simulation software. It is yours.
So it was said that abstracts could be submitted in German, and I thought, why not? Sorry about that. So in my talk, I want to present to you a use case where my colleagues and I in my department, mostly being mechanical engineers, but also physicists, try to embrace the RSE skills, the RSE tools and principles to the best of our ability. And I'd like to present this to you in the hope that we can afterwards discuss and you can make proposals on improvements. For the most part of this talk, what I will show is initiated, conceived, and realized by Fabian Schlegel, my co-author here. I'm today mainly promoting and assisting him. So first up, what is our research about? So our research is about the simulation of multi-phase flows, for which you can see some examples here. Multi-phase flow is anything where you have liquids, solids, gases flowing in the same domain, and they occur in a wide range of industries. So we have clients in the marine, in the nuclear sector, we have clients in the automotive sector. Here I'm showing mostly examples from process engineering, the client we're trying to chase. They have a lot of money, but they don't hand it out so easily. The challenges that are involved in doing these simulations are multifold. So in single phase flow simulations, one of the bigger challenges is turbulence modeling or resolving turbulence at an okay computational cost. But in multi-phase flows, well, we have interfaces between, for example, a gas and a liquid, and you want to track that interface. And at a certain point, your computational mesh is not fine anymore, sufficiently fine anymore, so you need to go to a statistical approach, but then you have all the physical modeling of the forces acting on the bubbles or particles that you don't resolve anymore. And then there's the remaining challenge of modeling the transfer between these two worlds. So that's what we're struggling with research-wise. And the code that we're using for that is a famous open source computational fluid dynamics library called OpenFOAM. It's a rather large project written in C++. It originates in the 90s by a guy named Henry Weller, chemical engineer who was sick of writing CFD code in Fortran and tried it in C++. And what came out is a domain-specific language where everything is tailored to writing CFD algorithms. So the classical example is the representation of a differential equation you see on the bottom left there. Why we're using it? My colleague Fabian states OpenFOAM is a tractor. It can do many things very robustly. It may not be that speedy in very specific things, but we can use it for a range of purposes. There's a large community in research and industry. And if you don't want to write in-house code, it's your best vehicle of prototyping new methods or models or idea. So OpenFOAM itself, I cannot speak more highly of it. It's extremely well maintained, unfortunately by only 2 main core developers, at least for the vanilla release that we are using. And they have an impressive pace in their developments, and it's for us really hard to follow. But the work they do is for the good. It improves usability, improves maintainability, but we really have to run after them for keeping our extensions, our add-on code up to date. And that is really tough if you at the same time want to focus on doing actual research and not just working on chasing them. And that means that many people stick to a certain version of OpenFOAM, and that is by no means a sustainable approach. So our mission that we're trying to accomplish since 5-6 years, something like that now, is to create a platform where we handle OpenFOAM code add-ons and particularly case setups in a sustainable way to allow continuous research. And a good example for that is some projects spitting out some OpenFOAM case setup. if you place that in some directory somewhere, forget it. If somebody wants to pick it up 5 years later, it's outdated, you cannot use it anymore. And we want to use it. We want to challenge new models based on that setup. So there has to be some continuity. And we have a good set of tools that we are relying on to supply this continuity, which HIFIS provides for us, the Helmholtz Federated IT Services. And there the most important tool for us is the self-hosted GitLab instance called Helmholtz Codebase. So we heavily rely on that, among other tools. And at this Codebase, we maintain several repositories. So there's research repositories. It's actually not just 2 of them, but we have multiple code repositories, multiple cases repositories. And then we have 2 utility repositories, for example, an infrastructure repository where we have templated CI/CD in them, which we can just include in the derived code and cases projects. And we tried to merge, we started trying to merge all Python code out of the code repository into something that we can deploy as a package, as a Python package, essentially. So our approach, as I said, is add-on development. So we have mainly these code and cases repositories. They are published via Rodare, the Rosendorf data repository, to obey most items of the FAIR principles. And they are developed in tandem in an agile fashion. We have a lot of tests, validation, and runs. And on the other hand, we take a fixed snapshot of OpenFOAM dev, the development line, from GitHub, and try to, as regularly as possible, update the commit chart that our add-on is based on. Occasionally, we also try to contribute things that has not been done so much in the more recent past, but the distant past we tried, but it's quite a lot of work to get code into that project. So it's not the classical pull request, and here I have a suggestion, and then it's merged in. That's not happening with OpenFOAM. So we serve out the code, so we have quite lengthy installation instructions, lengthy in the sense that we try to provide as many options as possible to our users. So first and foremost, the obvious compilation from sources. For anybody who cannot do anything else, basically, we also supply Debian package, which is very user-friendly, but not so much for developers. And Docker images are, of course, for us a backbone, mainly for all of the CI/CD jobs, but also for us for local development in a standardized environment, what Docker is essentially for. Headache is, however, I said that we're providing a platform, which means we also have clients, and these clients are not always allowed by the system admins to install Docker. Well, we tried going with Docker rootless for quite a while, also tried Docker desktop, but we have, for example, this issue that OpenFOAM setups often contain dynamic code elements which cannot be executed as root. OpenFOAM prohibits that. You can patch that, that's what we did, but that's not a good idea. So we need to run everything as a Docker user, and my colleague Fabian had quite a bit of headache with this because some reason rootless Docker has an issue that you cannot mount, change the permissions of directories that you mount to the container. So, so that's what with Docker. Something that we have also invested quite a bit of time in is creating the Docker files in a way that the Docker image that comes out of it is compatible with Aptainer for containerization on HPC. So currently we're compiling everything from sources, providing as modules as it is normal. But for us, we want to increasingly or completely switch to Aptainer because nightly building of this add-on on the cluster, if you've already built it in a pipeline, what for? It's duplication. But Aptainer poses, again, its own challenges, for example, MPI jobs. So you cannot, you have in an OpenFOAM setup, you have a range of serial tasks, and then you come to the parallel tasks, you want to jump out. You would have to jump out of the container for the MPI job because it's always MPI run minus NP, and then Aptena exec, and not the other way around, which is unfortunate for us. And it's also annoying that you have to either bind mount the MPI or have this hybrid approach, because that, yeah, there's no, that's not portable anymore if you can't supply your own MPI. We're currently working on a solution. There's new ideas on using the Slurm PMI process management interface for full containerization of MPI, and with some trickery you can make it portable, but I'm currently struggling in, with making things like InfiniBand work then. So I said we also want to be able to rerun simulations in a quick fashion. So what we did is we set up our cases repository as a snakemake workflow, so we can run all cases that are listed in a YAML file with simple commands, either locally or with Slurm to HPC. And that then spits out reports containing all plots that would otherwise be scattered across directories. And in CFD, the thing is you don't have a static reference solution always. So tiny things change in the core, you have subtle differences, so it's not the reference solution. It's somewhere you want to be close to a reference solution, and you also want to be able to update this reference solution. So lately we've tried to compute error metrics, so quantifying overall agreement in simple numbers, goodness parameter, so which we obtain via fuzzy logic out of several error metrics. So that's also a tool that we're relying on, snakemake. Sprint cycle upgrades, that's the greatest pain. So we're trying to chase after OpenFOAM dev, but the minute you caught up, it's gone already again. And the main problem is code is partially copied in our repository and modified. There's not an interface for everything, so you have a lot of manual labor to do. The discussion here is, would we do ourselves a favor if we rather fork and directly code in the OpenFOAM core and merge regularly from origin OpenFOAM dev? Are we doing ourselves a favor? We'll discuss. Now just 2 more slides with a peek on our pipelines. So that's a merge request pipeline that we have with some static checks on the left. Then a Docker image is built in the build job, which is then used for small unit tests. And this is also linked in a multi-project pipeline with the cases repository, where snakemake again executes all setups in a scalable manner on the GitLab runners. But that's just single time steps. What we want, what is our midterm goal, is a fully GitLab integrated validation pipeline, where we say we have the Docker images already built in the pipeline. These are pulled to HPC and converted into Aptena images, singularity images. And then jobs are submitted from basically submitted from the GitLab runners, if you like. And the high goal there is that with Aptena and snakemake, we reach portability and can serve our developments to clients in the most elegant way. To summarize, research on multi-phase flows, it requires continuity. That has been clear all along, but not many people are willing to invest the effort to actually make it continuous. But with the Helmholtz code base and with HiFiz, we have the tool set, the means that provides us with tools of doing so, and that makes such downstream developments actually doable. Remaining challenge that we have is how to efficiently pull in upstream developments. So maybe having something else than the sprint cycle upgrades. That's up for discussion. Thanks for listening. So, for questions.